Very good. Welcome to lecture number 5. The subject for today is going to be the Gaussian distribution. Uh, One of the amazing things about the Gaussian distribution is that it pops up everywhere. We're going to give at least 3 derivations of the Gaussian distribution in this course. And in part, the reason for doing that is for us to start appreciating more and more and more why it is that Gaussian distributions are so common. They appear in the distribution of experimental errors. This is how Gauss first came to think about the Gaussian distribution. This was early 1800s. In the late or 1860s or so, 50 years later, 60 years later, Maxwell figured out that the distribution of velocities in gases is the same as the distribution of experimental errors. So the Gaussian distribution is the Maxwell probability distribution for velocities. It's not just in gases, it's in liquids and solids. The distribution also appears in diffusion phenomena. It appears in the fluctuations of thermodynamic quantities. As we shall see towards the end of the course, it also appears in foundations of quantum mechanics in a very, very important way. So how is it that this comes about? What we're going to do today is start by deriving the Gaussian distribution as a limiting case of the binomial distribution. So let me switch over to my screen here. There we go. So let's recall the binomial distribution. The binomial distribution says that if you toss a coin n times with each with probability theta, then the probability of m heads is going to be given by a binomial coefficient. And then this factor, theta m, 1 minus theta n minus m. So what we would like to be able to do here is to study what happens, what is this distribution for large n. We want large n. What we saw was that the binomial distribution, if we're going to plot it, we plot here the probability of m, and this is the number m, and it goes all the way from 0 to n, and this is going to be some kind of something. The expected value, m, happens at n theta, and the width of this distribution is given by the square root of n theta 1 minus theta. We can plot this in terms of frequency. So if we plot frequency here, the frequency is defined as m over n. So what we're doing is exactly just plotting the same thing again, but instead in terms of the rescaled variable f. And in this way, the probabilities go, the range, the x-axis goes all the way from 0 to 1. And what we get here is some kind of curve. The mean frequency is theta, and the width of the distribution is theta 1 minus theta over n square root. So what we are seeing here is that the distribution is going to be getting narrower and narrower. Okay, that's the conclusion of having written that RMS deviation for the frequency. It gets, as n grows, this becomes narrower and narrower. So as n grows, this distribution here becomes more and more peaked around the mean. Now this is actually very nice because it means that if we want to figure out what the probability is for large n, essentially we know it's going to be 0 everywhere except at the mean. Except for a very, very tiny region, we know exactly what the probability is going to go. It's gonna be 0. Very good. So the whole region of interest is going to be what happens in this tiny region. Now, whenever you want to figure out the probability a function, whenever you want to approximate a function in a tiny region, the recipe is you use a Taylor expansion. Just expand about where the maximum happens, about the mean. Now, that's fine. We are going to expand about the mean, but you have to be very, very careful. If a little bit of change causes an incredible change in the function, then keeping the first, second terms in the Taylor expansion doesn't work so well. You have to keep many, 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 and that's not so useful. So how do we proceed? The fact that this function here varies so rapidly about the maximum means that a straightforward, naive Taylor expansion is not going to work very well. We're going to need very many terms. So what we're going to do is we do a dirty trick here. We say, well, the function p may vary very quickly in the vicinity of the maximum. But if we take the log, we can make its variation much smoother. So what we're going to do is we're going to take the log of p and we're going to do a Taylor expansion about the maximum. So here we have, well, I don't want to write the whole thing, but well, let's do it. We're going to say, well, expand about the maximum. This is going to be the log of p evaluated at the maximum plus the derivative of log p with respect to m evaluated at the maximum multiplied by the difference, m minus m0, plus 1/2 the second derivative of log of p with respect to m evaluated at the maximum, and then m minus m0 squared. So you see, and we could keep going. Now several questions arise here immediately, which is, okay, wait a minute, m is supposed to be an integer, so how do you take a derivative with respect to an integer? Well, our first trick here is going to be to recognize that when we have numbers that are so incredibly huge, because after all we're taking n to infinity, when we have these numbers that are so incredibly huge, a difference of m to m plus 1 is a very, very small difference, relative difference. And so we can sort of take the consider m to be a continuous variable. All these calculations can be done at the with different levels of mathematical rigor. That's why we're going to have to derive this a few times, but also different levels of mathematical rigor. And as you increase the rigor, you also decrease the intuitive understanding of what's actually going on. So what we're going to do next is First, realize also that, let me see, in this expression for the probability here, there, you're going to have factorials. How do you take derivatives of factorials? So what we're going to use is the Stilling approximation. And what that says is that for large m, the log of m factorial can be approximated by m log m minus m. And if you want, and you want to keep the next term, we don't need it, but actually it's instructive to keep it just for the sake of making a comment. 1/2 log 2 pi m. So now, the comment that I want to make is that for large m, this approximation is actually really very good. For m of the order of, say, 10 to the 23, right? Then clearly this term is of order 10 to the 23, right? It's that m multiplied by the log of m. So that's this term. Same thing happens with that term. But the last term is of the order of the log of 10 to the 23, which is something around 55. So if you think about it, you might think that a correction of 55 is completely irrelevant when the terms that you're talking about are of the order of 10 to the 23. So you have to take one of these terms and compute like 21, 22 digits in order to find a little bit of a difference. So that's why this approximation is actually very good. So what we're going to do now is we're going to write the log of p, which is the log of n factorial m n minus m factorial theta m1 minus theta n minus m. Expand the log of the first, log n factorial minus log m factorial, and this is these terms that we're going to use the Stilling approximation, minus log n minus m factorial plus m log theta plus n minus m log 1 minus theta. And so now we're going to do calculate the derivative of log of this quantity. What we need is to compute the various derivatives, the first derivative and the second derivative. So here we're going to, let's go. First, the derivative of the log n factorial, that's 0. It contains no n's. So we go to the derivative of the second. The log of n factorial is the log, the derivative of log n factorial is the ddm of that, which is the ddm of m log m minus m. I'm neglecting the very small, the much smaller third term. And what we do when we do that, we have the derivative of the first piece. That's going to be the log of m plus take the m and do the derivative of the log minus the derivative of the m, that's a 1, so this piece cancels that, and we see that the derivative of log n factorial is log m. So we're going to use that expression to do the d log p d m to write this as the derivative of log n factorial. So this is going to be minus log m. Then we do the next term. When we do the derivative of this guy here, this is going to be minus log n minus m. Just make sure you get it all correct. There is an extra minus sign here, which flips this guy around, and then we have plus the derivative of the log theta term, which is plus log theta, and then we have minus log 1 minus theta, and all of this can be now collected back into a log. Let me see, I'll put it here. This is going to be the log of theta n minus m, m1 minus theta. That's the first derivative. Now we do the second derivative. Second derivative. And it's easy to see how it goes. Take the derivative of the first term, that's 1 over m. Take the derivative there, you get something, and then these terms disappear. And so that derivative is going to be minus 1 over m minus 1 over n minus m, which is the same as minus n minus m. Very good. So now that we have those two derivatives, we just substitute here. Now, we want to expand about the maximum. So we want to choose M0. We want to choose M0 so that it is right at the maximum there. So choose M0, the point about which we are expanding, so that the derivative of log p at the maximum is 0. And what this means, if we go back, here's the derivative, this is this. So we want this guy here to be 0. The log of 1 gives you 0. So what we want is this quantity here to be 1. That determines what M0 is. So let me write it out. What we want is theta n minus M0 divided by M0, 1 minus theta equals to 1, which is the same as just solve. Let me see here. We have on the left hand side we have theta m0. On the right hand side we have m0 theta. Those two cancel out, and so we conclude that m0 is n theta, which is equal to the expected value of m. Now we substitute back into the second derivative. So we want to substitute that m0 into the second derivative here. Just put m0 here and m0 there. And for the second derivative, we conclude this is going to be um, second derivative evaluated at m0. This is going to be, once you do the calculation, it's going to be n theta 1 minus theta, which is equal to minus 1 over the variance squared. So we're done. Let's see what we obtain. Therefore, our expansion has yielded the following. The log of p is the log of, let's just go back to the expression we had here before. Let me see, what expression? This one here. Where is it? One more. There, this is the one. We want to, this expression here at the bottom. We want to expand log p. We have the 0th order term, which is log p evaluated at 0. Then we have the first order term. This is being evaluated at the maximum where the derivative vanishes, so this disappears. And then now we're going to have that third term there. So here we go. The answer is log p is log p of m. This is log p evaluated at the maximum, which is the expected value, minus 1/2 the second derivative, plus 1/2 the second derivative, which is minus 1 over the frequency, the variance squared, the variance. So this is minus 1 over delta m squared with that 1/2 multiplied by m minus m0 all squared. So when we actually write it out, take the exponentials on both sides, what we find is that for large m, this is going to be the p, the probability evaluated at the expected value multiplied by the exponential of minus, here we have m minus m squared over 2 delta m squared. And we're done. There is one extra thing we would like to do, which is we would like to be able to figure out what that probability is at the maximum in order to have the full probability distribution. One way to do it is just to go back to the binomial distribution and substitute. Another way is to realize that what we have here is the probability of m. The variable that we're computing the probability is the number of heads, probability of m. This object here is just a constant, right? While all the dependence on m is contained back here. So one of the things we could actually do in order to depend on this overall constant is recognize that this overall constant is just a normalization. So to find what this object here is, just impose that the probability be normalized, imposed normalization. And this is how we go about doing that. We write, well, 1 is supposed to be the sum over all m's p of m. But this is approximately equal to, because remember, the capital N is absolutely huge, and each increment from little m to m plus 1 is just like a minor correction. So we're going to write that as an integral from all the way from 0 to n of px dx. And because the probability distribution here is such something that goes up and down, whether we stop at 0 and go all the way to n, 0 to n, clearly there is nothing out there, nothing out there, so we're going to write this basically as minus infinity to plus infinity px dx. So now we look up the formula for how do you integrate Gaussians, and what we use is minus infinity to e plus infinity, the integral of minus alpha x squared dx. You can just go ahead and look it up in a table. It's pi over alpha, and so we use that function to get that the overall normalization constant is equal to 1 over 2 pi the variance squared square root. So we're done. Conclusion, the probability of m is given by 1 over 2m square root exponential of minus m minus the mean squared divided by 2 delta m squared. This is called the de Moivre that's a V, Laplace theorem. And this is a formula that we're going to use so much that you end up remembering in by heart. That is the square root of 2 pi. That is the square root of the variance squared. So, well, so it's just the RMS deviation that appears there. What appears in the exponent is the full variance. So this is it. When you have a binomial distribution and the number of trials is infinitely large, the probability distribution approaches a Gaussian, also called a normal distribution. We can express this, and I'll leave you guys to do this as an exercise. We can obtain change variables, and instead of talking about m, we can talk about frequencies. So for frequencies, so just replace m by nf, and you can find the corresponding probability distribution. The probability distribution for the frequency is going to be 1 over 2 pi, and here we're going to have the appropriate variance exponential of minus frequency minus the expected value of the frequency, which is theta, divided by twice the variance of the frequency, where this sigma is going to be theta 1 minus theta divided by n. Very good. Let me do a quick example of something like this. Suppose, so here we go, an example. Suppose that we have a quantity. Suppose the quantity x is given by the sum of very many small contributions. Very many, so this is from n equals 1 or 1. Yeah, why not? Doesn't matter. It's to n, many contributions that are small. Where the quantity c, the quantities c are statistically independent. And the expected value of any one of these c's is actually very small. So wait. C is equal to epsilon with probability theta, and it's equal to 0 with probability 1 minus theta. So what you have here is a bunch of quantities that are very tiny, and the quantities can be epsilon or 0. And they happen with probability theta and 1 minus theta. Here is one possibility. Imagine that you're walking and your steps are very tiny. So either you walk a step epsilon or you don't. And see what is the probability of the sum. How many, what kind of distance have you accumulated after n of these steps? Here's another possibility. You're trying to measure the length of a ruler. And of course, the ruler is made up of atoms, and the atoms may be doing something wacky. And so the question is, what is the length of the ruler? Well, it depends on the displacements of each one of those atoms. But the displacements of the atoms are very tiny. So it would be, that's the kind of thing that you would model, the length of the ruler as the sum of the distances, the increments due to each atom. So what when we do that, then let the expected value of x, this is going to be n times the expected value of each one of the x's, which in this case it's going to be yes, the expected value of x's is going to be n. It's going to be, let's just do it, right? Epsilon with probability theta plus 0 with probability 1 minus theta. So this is going to be n theta times epsilon. So you can see here the number of successful outcomes showing up there again. So that's the expected value of x. The expected the x itself is going to be a certain number m of epsilons. And so when we ask, what is the probability? So this is the question we want to ask. What is the probability that after n terms in the sum, the value of x lies within a small range which is x in this case is m epsilon minus some small range m epsilon plus some small range. And just like we changed variables earlier to go from the m expression into the frequency expression here, we can actually go from the m expression for the probability to the x expression and write down something like dx dx is equal to 1 over 2 pi the variance of x square root exponential minus x minus its expected value squared over 2 variance of x squared, where the expected value of x is going to be the mean value of m's multiplied by epsilon, and the variance of x is going to be the variance of the m's multiplied by epsilon squared. So this is now you see why it is that the Gaussian distribution is going to be so universally common. Whenever you have a macroscopic variable that's written in terms of a large number of contributions that are of microscopic size, then the distribution for the macroscopic variable is going to be given by Gaussian. This explains why Gaussians appear in thermodynamic fluctuations, because typically a thermodynamic fluctuation is going to arise. A thermodynamic fluctuation in energy. Well, the total energy of the system is going to be given by adding the energies of individual atoms. So that's exactly the kind of thing that you're doing here. It also appears in the classical limit of quantum mechanics. If you're asking for what is the probability distribution for the center of mass, then you have to add over all the atoms in the system. Again, you get distributions of this type. It appears everywhere. But there were two assumptions here that were absolutely crucial. One of them was that all these variables, the x's, had the same mean, same probabilities. The probability for each one of the microscopic variables was exactly the same as every other one. Same average and same variance. And that led here. So one assumption was identical distributions. The other assumption was independence. So what we're going to show next is the next level of the deriving Gaussian distributions is what happens if the distributions are not identical. It turns out to be the case that you still get the Gaussian. And in fact, but we still, in this derivation, we're going to continue to assume that each one of the variables is independent of all the others, right? They're all independent. But it's even possible to consider situations in which the variables are not independent and you still get the Gaussian. So that's why this thing is like really shows up everywhere. So let us look at what happens when we do what's called the central limit theorem. This is where we give up on the requirement that the various small quantities be identically distributed. So here we go. We consider the sum. Again, what we have is a sum. Consider the sum. X equals capital X. Okay, my symbol for capital X is always going to be something like that. And the real reason is that uppercase X and lowercase x are very easy to confuse. And so I don't want to confuse them. And so I'm going to have a special symbol. It's like a Roman digit for number 10. That's going to be my capital X. And then here I'm going to sum all the small x's when r is going from 1 to an n. And what I would like to do is figure out the probability distribution for the macroscopic variable. So what do we know? Where the xr, x1, xn are independent. However, but not identically distributed. But not identically distributed. Okay, in order to figure out the probability of capital X, we do need to know something about the distribution of the micro variables. And so we're going to assume the following. We are going to assume that the expected value of XR is known, mu R, and that the variance of XR is also known. We're going to call it sigma R. Notice that they depend on R, so that all of these microvariables have different distributions with different means and different variances. And in particular, these probability distributions do not have to be binomial. The distributions, okay, the probability of XR need not be binomial. It can be anything you want. Anything you want, provided there is a mean and there is a variance. So, very good. So how do we compute the probability of the sum, given that you have the probability of the various terms in the sum? For that, we use the following magic formula. The probability of, after n sums of the macroscopic variable, this is the probability density, and I ought to write the dx here, but I'm not going to, just because the dx is going to appear on both sides of the equation. And so the way we do that is we sum over all the probabilities of the probability of x1, x2, xn. Now notice what I have done here. I'm summing because I'm trying to figure out what the probability for this macro variable is, and I'm going to sum the probabilities of everybody. Notice how the probabilities for all the microscopic ones are in the form of a product. That's where I'm saying they're independent. But now I'm going to say that the probability distributions are different. And so there is a probability P1 for variable 1, 2 for variable 2, n for variable n. And what I'm going to integrate is a delta function that gives 0 except when x is given by the sum. So that's the way you compute the probability of a function. You do this. This is called the this expression that I have here. This delta is called an indicator function. So the probability of x, probability of a function, in this case the sum, is equal to the expected value. You can see that we're integrating over all the probabilities, so it's an expected value of the indicator function. Oops. Of the function x, of x. The indicator function is a function that tends to be 0 when the function is not obeyed, and it's not 0 when it is obeyed. So the derivation of formulas like this is part of a homework problem, and I'll let you figure out how that works out. This is a useful trick. Now, how does one solve such an integral? Figuring out that integral is not completely trivial. You can do it using Fourier transforms. The Fourier transforms of deltas are very simple. The Fourier transforms of some of those are also not necessarily complicated. In any case, there are ways to do it. It's in the lecture notes, so please look it up. But before we proceed, we would like to show this, to indicate here that there is a little bit of a problem. And the problem is that when n, so this is a technical problem. The technical problem is that if you're going to compute the limit as n goes to infinity of the expected value of x, when you have n terms in the sum, this limit is going to be equal to the limit n going to infinity of, look at x. The expected value of x is going to be the expected value of the xr's. So this is going to be the sum of r equals 1 to n of the expected values that we have here. And now you see what the problem is. If these guys are any kind of number at all, if these guys are any kind of, let's say, for example, the expected value is constant, like we saw for the binomial, then the limit as n goes to infinity diverges and does not exist. So, technical problem. For important physical probability distributions here, for important physical probability distributions such as binomials, this limit does not exist. Similarly, the limit as n goes to infinity of the variance of x I don't know how this for given n, this is going to be the limit as n goes to infinity. Now remember, these guys here are independent variables. We already saw that when you have a sum of independent variables, the variance of the sum is the sum of the variances. So this is going to be something like that. And so now you see that you have a real problem again, right? These limits do not exist. The limits do not exist. So how do we solve this problem? This is the trick. Solution. Consider the following scaled variable. Instead of the variable x, consider the variable y, which is the original x, and we're going to subtract the sum of the means. So this is the sum of the means, mu r, for r equals 1 to n, and we're going to rescale it by the sum of the square root of that's an s, the square root of the sum of the variances. Now you see that while it is true that this guy, the average of this might diverge, well, we're subtracting the average, and we're rescaling by something that might also diverge, and so hopefully all the infinities that were appearing or would appear in these various terms are also canceling each other. And so when you do that, then the probability for this scaled variable y, well, we have in a particular range dy dy, is actually by definition going to be exactly the probability for the original x dx. So when I compute what the probability of this dy is going to be, the method of just changing variables, but the method of indicator functions tells me this is going to be px1 pnxn, and then there is going to be a delta function. Maybe I should write it over here. Delta function of y minus, and here we're going to have the scale variables. Xr minus mu r divided by Sn. So this is the result. Do the transformation exercise, do the transformation. You're going to have to worry about what happens when you have terms in a delta function, like things like this. This is equal to delta x over a. You gotta worry about some of those things, but this is the result. And now the issue is compute this integral. This requires can be done in different ways, but one convenient way is to use Fourier transforms. I have it in the book. The result is the following. So here we go. The conclusion. I'm not going to do the proof, but the conclusion is that. And this is called the central limit theorem. The central limit theorem. And what the central limit theorem says is that if you have independent variables, x1, xn, with means mu r and variances sigma r squared, then variances which and they satisfy the following Lyapunov condition. Lyapunov condition. And what the Lyapunov condition says is the following: the limit as n goes to infinity of 1 over Sn cubed. Let's remind yourself what the Sn is. It's just the Sn squared is the sum of the variances. So of the sum R1 to n of the expected value of xr minus mu r cubed. So let's see what we're writing here. Sn squared is just the sum of the variances. What we have here is the sum of not of the deviations from the mean squared, but cubed. So this is like a third moment, and we're dividing by the variances to the power 3. So this is looking at, this was looking at the first moment. This is the second moment. What we are looking at here is how does the third moment of these distributions behave. And well, the condition is that this limit is 0. If those limits go to 0, then the limit of the probability distribution for y as n goes to infinity, which is what we're going to call py, is equal to 1 over root 2 pi e minus y squared over 2, which is Gaussian with mean expected value of y is 0 and the variance of y is equal to 1. So this scaled variable has a very, very simple probability distribution. Maybe it's time to stop here. So, conclusion, to summarize, why do we care about probability distributions like the Gaussian distribution? Basically, it's because whenever you have a variable that is composed by summing very many small contributions, the effective probability distribution for the sum is going to be Gaussian. This tends to happen whenever you have a macroscopic object, macroscopic variable that's composed of many microscopic contributions. And this is very general. You require sort of like certain conditions of independence, and as we saw, you require also that higher order moments in the distribution of the individual variables do not add up too much. So when is it that we're going to obtain Gaussians? We're essentially going to obtain Gaussians when the information that is relevant to our problem is contained in the first 2 moments of the distribution. When the information contained in the third and higher moments happens to be irrelevant. And that, fortunately, is very common. Very good. In the next section of this lecture, we're going to start tackling the problem of if you have probabilities and you acquire data, how do you update? We're going to start talking about Bayes' theorem. See you then.